Good morning. Today we are going to look at minimization problem, just like maximization problem, which we had earlier solved. I'm not going to explain the formulation of the problem in detail as I had explained in the maximization problem. I've taken a problem from Anderson Sweeney to demonstrate a minimization problem. It's about M&D chemicals, which manufactures two types of raw materials, A and B, and supplies to soap manufacturing companies. Now, other details given are just listed down here. Each unit of A requires processing time of 2 hours, and each unit of B requires processing time of 1 hour in processing department, and the processing department has got 600 hours as its resource. And there is one production constraint which says that both put together, A and B, we have to manufacture at least 350 gallons. And there is one more constraint, customer requirement constraint, wherein a particular customer has asked for 125 gallons of A. Given this, how to formulate the problem and solve it graphically is what I am going to demonstrate today. As I had already mentioned in my maximization problem video, there are three components in formulating a linear programming problem. First component being defining decision variables, as I have defined here. My decision variables are A and B. A stands for number of units of A to be manufactured, raw material A to be manufactured. B stands for number of units of raw material B to be manufactured. This is the first component of linear programming formulation. Coming to second component, which is mentioning the objective function. Here I have mentioned as my objective function as z is equal to 2a plus 3b, because every unit of A costs us 2 rupees, $2 is the production cost per gallon, and $3 is the production cost per gallon. So if I manufacture A units of raw material A, then it will be 2A, and if I manufacture B units of raw material B, it will be 3B. So this will be my total cost. I'll just change the color. So this will be my total cost. So I will have to minimize this total cost. After mentioning the objective function, now we will have to list down the constraints with the given data. So the first constraint talks about processing time of 600 hours. Every unit of A requires 2 hours, and every unit of B requires 1 hour. If I manufacture A units of A, then time taken to manufacture A units of A will be 2A, and time taken to manufacture B units of B will be 1B, which should be less than or equal to 600 hours. It's the first constraint. Second constraint would be production constraint, which says that both together we have to manufacture at least, when I say at least, it should be greater than or equal to 350 gallons, because at least means that I have to manufacture minimum 350 gallons. More than that is okay, but less than that wouldn't be okay. And similarly, there is one more customer requirement constraint, which says that I have to supply 125 gallons. Here too we use greater than or equal to constraint, because it's typical demand. Demand is usually mentioned with greater than or equal to constraint, but never less than or equal to constraint, because not frame a constraint with less than or equal to inequality, because it would meet lesser than the demand, which is very odd in business environment. So whenever there is a demand, always use greater than or equal to constraint and not less than or equal to constraint. And finally, non-equality constraint, non-negativity constraint, which says that A and B should be greater than or equal to 0, which restricts us to only positive values, which graphically it means that it restricts us only to the first quadrant. Now this is my processing time constraint. I'll just scroll. Processing time constraint. This is production constraint, and finally this is customer requirement constraint. This is just for reference sake. Now after having listed down the constraints, we'll solve this graphically. In order to solve this graphically, what I'll do is that I'll first take the first constraint and then plot the equation part of the first constraint, and then find a feasible region which satisfies the inequality part of the first constraint. In order to plot the equation part of the first constraint, I'll take this, write this down as an equation, that is this equal to 600, and then plot it on the graph by finding 2 points. If I got 2 points, then I can easily plot. So I'll insert A is equal to 0 and then find B is equal to 600, which means that this is 0, 600 points. And when B is equal to 0, if I insert B is equal to 0, I would get A is equal to 300. So my second point is 300, 0. This is my 2 points. These are my 2 points to plot the first constraint. Similarly, I find 2 points to plot the second constraint. A plus B is equal to 350, the equation part, 350. Insert A is equal to 0. In fact, you can insert A is equal to any number, not only 0, but A would, inserting 0 would make my life easy. So B is equal to 350. So I insert 0. We will come across a situation wherein I will show you we cannot insert 0. When you insert 0, we might get B negative value, which is not allowed because of this non-negative constraint. In such situations, we insert some other numbers to avoid getting negative numbers. Now insert B is equal to 0 here and get A is equal to 350. So my 2 points for this constraint are 0, 350 and 350, 0. And finally we have got the third constraint. If I take the equation part, it is going to be A is equal to 125. So not much here because I don't have B component, so it's a straightforward A is equal to 125. Yeah, I've drawn a graph here. So what I will do is that first I'll plot the first constraint, which when I've got 2 points, 0, 600 and 300, 0. So first let me plot that. 0, 600 is somewhere here, and 300, 0 is somewhere here. So I'll connect these 2 points and then get my first line. Once I get my first line, this satisfies the equation but not the inequality part. Now to satisfy the inequality part, what I'll do is that I'll take 1 point below this line. Instead of taking some point, I'll take origin, which is 0, 0, which is also below this line, and insert this in this inequality. So if A is equal to 0, B is equal to 0, this whole left hand side will be 0, which is definitely less than 600, which means that origin satisfies the inequality part, which also means that any point below this line would satisfy the inequality, the first constraint. So I'll mark this region in order to show that all this is feasible region. when I say feasible region, pick any point in this region will definitely satisfy the first inequality. But it is not true if I pick some point above the line, and it definitely will not satisfy the inequality. So after plotting the first line, I'll plot the second line wherein I got 2 points 0, 3, 50. I'll use different color. Let me use red. Change it to red. 0, 350 is somewhere here, and 350 is here. I'll connect these 2 points. Okay, let me change the point. 350. This is not good. Let me redraw this. Okay. It's not straight, but assume that this is a straight line. Now if I similarly pick 0, 0 here and insert in this second constraint, I would get 0 left hand side, which is not greater than 350, which means that origin doesn't satisfy the inequality, which also means that any point below this line would not satisfy the inequality. If you pick some point above this line, it will definitely satisfy the inequality, which means that the feasible region for this second constraint would be this entire this region, which is in fact infinite region. And now the third inequality says that here 125, a is equal to 125. You can see this. So third constraint. Let me show you. If I have to plot this third constraint, it is just pick 125 here. Let me choose a different color. Let me choose green for change, and then draw a parallel line to the y-axis, which gives me the third constraint. Plotting the third constraint, a is equal to 125. This is third constraint. Why we have drawn a parallel line to y-axis is because this a is equal to 125 is nothing but for any value of b. Let me change the color to yellow, and then mention this as b and this as a, x-axis as a. Now, for any point of a, for any value of b, whether it is 50, 100, 150, 200, a would always be 125. Actually, this constraint can be written as 1a plus 0b is equal to 125, which means that if you put 0, 50, 100, 150 here in place of b, a would always be 125, because of which we get a parallel line like this to the y-axis. After having drawn the third constraint, and then mark, if I have to check the inequality part of the third constraint, a greater than or equal to 125. If I put origin here, a is equal to 0, 0 is definitely not greater than 125, which means that the feasible region would lie to the right of the third constraint, and I'll mark the feasible region like this for the third constraint. Now if you observe the feasible regions of all the lines, the only feasible region which satisfies all the three constraints would be this triangle. I'll mark the triangle with blue color and this triangle, because this is the triangle where you can observe that inside this triangle all the three colors meet, in the sense that this is a common region, while pick any other area which is not common region to all the three constraints. Might be a common region for one or two constraints, but not for three. Only this triangle gives us a common region where any point if you pick in from this region will satisfy all the three constraints. After having picked the common region, now I'll have to find the value of these three corner points, which might give us a minimum value, because the problem is to minimize the objective function. Now this point would be straightforward because it's the intersection of third constraint and the first constraint. So what I'll do is that I'll just insert a is equal to 125 in the first constraint, first equation, and get b value. So if a is equal to 125, 125 into 2 is 250. So b is equal to 600 minus 250, which is around 350. So this point would be 350, 125, 350 would be the first point, this point. And this again, you can see that 125 is equal to 125 because it falls on the third constraint, is equal to 125. But intersection of third and the second constraint, so insert a is equal to 125 in the second constraint, second equation, and get b value. So if a is equal to 125, b would be 225. So 125 comma 225 is my second point. Third point is intersection of first and third constraint. Yeah, so this third point is intersection of first and second constraint, which I have written here, equations. So if you take this as intersection, solving by simultaneous equations, I would get a is equal to 250 here, and inserting 250 in this equation or this equation, I would get b is equal to 100. So this third point is 250 comma 100. Now that I got 3 points, I'll just insert all these 3 points in my objective function, which is z is equal to 2a plus 3b, which I have to minimize. So the first point is 125, 350, which gives me 2 into 125 plus 3 into 350, which is around 250 plus 1050, gives me 1300 as my total cost. The second point is 125, 225. So inserting this in the objective function, it will be 2 into 125 plus 3 into 225, which gives me 250 plus 645, which is 59895, which is definitely less than 1300. Finally insert 250 and 100 in the objective function, which gives me 500 plus 300, 800 as my total cost, which is definitely less than these 2 points. So my optimal point would be this one, which gives me the most minimal cost, and asking us to manufacture 250 units of A and 100 units of B, so that we meet all the constraints and produce the minimal cost. Thank you for watching my video. Bye.